Jul here in Barcelona. I am a researcher in the group of Smart Society, and my background is in business, but I am especially interested in the social construction of technologies, so technologies and innovation, but not the technical part. So everything related to the more socio-technical system that it implies. And well, today I'm gonna present a little bit about the barriers of scalability of quantum computers from a critical perspective from science and technology studies, which is the field I mostly focus on, the intersection between science and society. So any questions you may have, you can interrupt me or at the end, however you prefer. So as a small introduction, uh, quantum technologies, I think we're going to relate in this industry that it is often described as an engineering challenge by a lot of people in this industry, whether they're scientists or not. Even physicists usually tell me, well, the physics it's already there, right? Now the gap is for the engineers to try to fill it in. So a lot of this perspective is what it's been talked around lately in the discourse. And the main challenge is entering and improving qubit coherence, reducing the error rates to develop, scalable error correction systems. However, and in the practice, I find that in many industries and scientific discussions, the assumption is that once these technical problems are solved, large-scale quantum computing would naturally follow. And this is concerning because this suggests that scalability it's only a technical issue. And what I want to present today is that it is not only a technical issue, it goes further. So, for instance, uh, building a quantum system at scale also require major expansions in energy infrastructure, rare materials, industrial capacity, and institutional support. As probably we can see more tangible here in the European Union bloc, the institutional support becomes very important in terms of the financing different projects and different research institutions. So it is not merely a technical issue, the scalability of quantum computers. It implies lots of different actors in lots of different areas. So these dynamics of economy can become a little bit more complicated beyond the science that relies on this technology. So moving on, current superconducting computers from IBM and Google already depend on operating at extreme temperatures and also highly controlled laboratory environments and very niche and specific needs that are highly demanding. IBM's roadmap toward processors containing thousands of qubits will imply not only more powerful chips, but also larger cooling systems, more complex wiring, and growing energy requirements. And this, again, we must see it not necessarily as a technical, but more as an infrastructural challenge. So from the perspective of science and technology studies, which is my field, or the field that I study, this matters because technologies not only scale through the technical efficiency alone, it also relies on large technological systems that need a expanding infrastructure, institutions, political priorities that align around them, for instance, because if this is not in the agenda of the state or the government, we would very hardly be developing or research towards that. Um, this is to note, it's very different here in the European Union, which is more based at the European Commission's agenda. So we're lucky that in that aspect, it's something that they keep into account. But if we talk of other parts of the world, say the United States, a lot of it is developed by private companies, as we've seen before. And well, the shift of attention away from, only the qubit towards more broader systems to sustain this quantum competition is very important because it not only gives focus to the technical but the non-technical aspect. So in this sense, the when we refer to the quantum energy and everything that implies from this field, we should not only refer to the electricity that's consumed during computation itself, but also the wider infrastructure required for the cryogenic cooling, the semiconductors fabrications, materials extractions, data center integrations. It expands more and more as we talk about this itself. It's not only the machine. Quantum technologies are not simply a new computational technology. It's also an emerging energy-intensive infrastructure that it requires not only the technical part, but society, fundings, policymakers, the involvement of government leaders, and so on. And well, this argument may become probably more clear when we view historically. I don't know if anyone in the room has ever read More and More and More by Jean-Baptiste Fresos. It's a book I recommend. He touches very nice points that he goes along when talking about energy and the different develops of energy throughout history. He makes a great point when he argues that new technologies rarely replace older systems through simple gains in efficiency. He says that instead, these industrial societies tend to just accumulate infrastructures over time, increasing the total energy use rather than reducing it. And we can see some historical energy transitions that may support this argument that he publishes in the book. And when there was the shift from wood to coal, it became even more and more used the wood for the infrastructure of the mines to keep them up. So we didn't eliminate the wood and instead transferred totally to coal. It didn't replace it. And the same happened from coal to oil. It did not eliminate the coal consumption. And the expansion of digital technologies, as people predicted back then, instead of uh, dematerializing economies. Instead, this digitalization revolution that we went through produced massive data centers, new supply chains, and rising electricity demands. So not to say a quantum computer will specifically go into this direction, but he shows that there's a tendency of stacking up or piling up different technologies on top of others. And this is something to consider because quantum computing may follow a similar path. Because even if quantum processors eventually solve some problems faster than classical computers, the infrastructure needed to support them may significantly increase the overall material and energy consumption. And this is something that has happened historically with these previous examples, and it can easily happen with quantum computer. Not always we see a technology that simply replace another one with a completely new, but maybe creates new ways of needs and demands of different resources. And this is, I think he makes a great point in raising this, and this can be something that scholars um, nowadays can infer that may happen to quantum computing, and not only quantum computer, different emerging technologies as well, even if we talk about solar panels and so on. And there is already some empirical signs of this problem, if you want to say. Um, well, there's superconducting quantum systems already require multiple cooling stages, thousands of cables connecting room temperatures to electronic cryogenic processors and so on. And as qubit numbers increase, these systems may become more and more difficult to cool and stabilize, right? So researchers of the National Renewable Energy Laboratory have argued that those cooling requirements may become one of the main barriers to scalable quantum computing because these systems consume large amounts of continuous power while remaining relatively inefficient, especially if we compare it to, classical computation. And fault-tolerant quantum computing cloud require millions of physical qubits to create, stable logical qubits. So it just shows that the demands, whether right now that is not as efficient, and even if it's efficient at some point, scalability involves much more than increasing the computational power. It also means expanding the energy and the industrial system that supports those quantum devices. And if we move on to the material dimensions aspect, if you want to say, um, quantum computing have also changed over time. In the early 90s, experiments were small scale laboratory projects involving also limited numbers of qubits. Today, technologies are increasingly tied to the national security strategies in different countries, industrial competition, and global technology policy. Governments, for instance, like the United States, China, European Union, now invest heavily in quantum research as part of a broader geopolitical competition over computing and cybersecurity. And as a result, quantum development increasingly depends on semiconductor manufacturing, helium supply chains, specialized fabrication facilities, and cloud computing infrastructures. And if we talk about the European Union, we can see we are not completely able to cover all of these areas. And as you can see in some agendas of the European Union, when we talk about technology, the sovereignty, being self-sufficient, this becomes more and more difficult as every country wants to be self-sufficient in these technologies and in these supply chains, and it can become more and more complex the more you take into account the complex and the political tensions that we're living nowadays between different blocs. But this is precisely one of those major challenges. And also quantum computing may reinforce similar, you know, concentrations of power. If we think of, for instance, some science and technology scholars describe this as an infrastructural momentum, that once the technologies become embedded in industrial and political systems, they create long-term dependencies that shape the future development, just as the design, the development, and the deployment, which is something that I didn't particularly put on here, but also the deployment of these type of technologies. So they are very tied to these geopolitical dimensions. And also, questions of energy and infrastructure also raise political issues. Scholars like Mitchell argue that energy systems are a form of political organizations because they shape who controls resources and who benefits from technological development. Quantum computer can reinforce those tensions or concentrations of power. The high cost of cryogenic systems, the fabrication plants, the advanced research facilities mean that only a small number of governments and corporations currently have the capacity to build large-scale quantum infrastructure. I mean, this is a truth. It's just something that not any country can just start deciding to do it without the specifics, limitations that budget has or that corporations have. Some corporations have more access or power towards developing and researching these kind of things, especially aid by military in some countries. Um, and at the same time, quantum technologies rely on these fragile global supply chains involving like the rare materials mentioned before, semiconductor manufacturing, the helium. I know in this case in the Barcelona Supercomputing Center, they're very proud to say that the quantum computer itself provided by Kilimanjaro, it's a European Union made machine right now. However, they are aware that the resources to maintain or keep going, for instance, helium-3, that's a big component of it. They have to buy it from, if I'm not wrong, Russia. So this creates these limitations where we as a country, I mean, which countries or blocks of regions can try to handle the sovereignty, but the supply chains are so complex and the materials can be so rare that it makes it almost impossible for this. So scalability depends not only on the scientific progress, but also on the geopolitical stability and industrial coordination that countries may have. And another aspect that I think is very important for the scalability is when we talk about the public legitimacy, because this shapes how technologies develop. Historical examples such as nuclear power show that, technically advanced systems can still face resistance because of concerns about risk, about governance, or even environmental impact. And quantum technologies may encounter similar tensions. For instance, the public discussion, probably from people in not the scientific field, but more in the social civilian way, people their discussion shifts from being between optimistic claims about the breakthroughs of medicine and climate modeling, and also the fears concerning surveillance, cryptography, military competition. So this is like the duality that exists between people, and without the people acceptance or the legitimacy, can be very, very difficult to break through into scalable into a scalable technology. And this means that scalability is, again, not a matter of only a technical performance, but it also depends on whether quantum technologies are seen as socially useful, environmental sustainable, and politically trustworthy. So to end this discussion, I think I've touched several different points of barriers from the non-technical aspect, barriers for scalability, but I just want to end that from this perspective. I think the key issue is not only whether quantum systems can become more efficient, because they could, but what kinds of infrastructure and energy demands these expansions will produce, and if we're able to respond to those demands. Also, the technical metrics such as qubit fidelity or computational speed capture only one part of the picture, because it's often overlooked the broader questions about energy consumptions, resource extraction, the sustainability, the concentration of technological power that can rely on hands of different corporations or countries. So I just want to end the presentation saying that the challenge is not simply whether quantum computer can scale, but what kind of socio-technical system will emerge as it does scale into society. Whether we are prepared to respond to those demands, whether countries are prepared to coordinate, whether we have such a fragile supply chain that this may or may not even become possible. So yeah, now we have 10 minutes. I don't know if you have any questions or thoughts. Thank you very much for listening. And yeah, if you have any comments, I will also be there tomorrow and Friday again, and we can further discuss. But I've tried to keep it a little bit tight. And I know I come from a very different field, so if you have any questions as well of concepts or whatever, I'm happy to explain or share with you thoughts.
Thank you. Is there any question from the room? From all the way back. Okay, 1 second, Nelly.
Thank you. When I'm talking with policymakers, they are trying to go for this AI independence, and their biggest concern is that the data centers require lots of water. That is the bigger concern. The second concern is that they create lots of pollution due to diesel generators, and the third concern is the sound. They are not concerned about scarcity or the complexity of the supply chain. So is it possible to, let's say, promote to policymakers these quantum solutions as things that don't require that much water, or maybe it will make less noise?
Can you repeat? Is it possible to? Yes, yes.
I can repeat the question if you want. Okay. Yeah, okay. So how about, can you hear me now?
Well, I also, yes, yeah, yeah.
Okay, so my question is that the
Um,
policymakers, yeah, no, you cannot. Okay, so I will ask later. Okay, so the policymakers, like the, I don't know, ministers, they are more concerned about water usage, the diesel pollution generation due to generators, and sound more than anything else. They are not that much concerned about the energy. They are not that much concerned about the helium. So is it possible to sell these quantum computers to the ministers and policymakers as things that don't require that much water and they will not generate that much sound?
okay, yes, I heard you now correctly. Um, in regards to the policymakers, and often is probably the field I focus mostly on, right? The intersection between science and society. So here's where policymakers should take much more of a lead or an action. And it is true. Sometimes policymakers may worry about not the pertinent things to worry about, or they might think of threats. Often, policymakers, what they try to do is make acts like the AI Act, the Quantum Act, and so on. They propose acts or laws to prevent um, future threats for society or environment or so on. And I think one of the main weaknesses when we talk about policymakers in regards of making laws and rules for technologies is precisely that, and this is very critiqued in my field, that there is very little involvement of the policymakers going into research centers and understanding the technology itself. Because policymakers don't overlap as much as they should in order to understand the real concerns of a technology. What are the real challenges, the barriers, or the immediate impacts that it may have? And instead, policymakers nowadays, they try to predict, and this is because of, how AI basically collapsed in our eyes and they didn't have any regulations or standardizations. So eh, policymakers try to predict, and they fail very much at predicting. But what I critique is that they probably fail not because prediction is already hard, right? It's very hard to try to challenge those future disadvantages or threats, but because they lack the preparation of understanding the technology, involving with the scientific researchers, and understanding what are the real concerns. So I think, and in my field, it is very criticized how the practice of some policymakers can be very limited or just very very weak in that sense, and they probably worry more about water, as you were saying, rather than other major concerns. As it can be, well, also in different countries, it can be of major concern the pollution, it can be of major concern the electricity or the energy consumption or the extractions themselves. But yes, it is a question I can basically not completely answer, but I think it gives you a big leap into understanding from my field how criticized these policymakers can be about a wide range of things like this, and not only in the European Union. I also talk about different regions. It's very hard for them to target appropriately what they're supposed to be regulating. So this is a kind of a duality, because if not them, who, right? So I think it is the lack of involvement that they have truly in understanding, in engaging with these scientific seminars or scientific, research conventions. At the end of the day, I try to attend, and I see the vast majority is either engineers and physicists, but very, few policymakers, which are also a very big part of it, right? They are the ones that should also be in the first line.
That's true. If I might just follow up, asking a question on like a direct follow-up, because now we've been criticizing the policymakers that are not coming to our events, which is true. There are no policymakers here, for example. But what is our responsibility as scientists? How do we touch them? How do we get them to come? And maybe, do you think there is something to criticize on our attitude as well? Because sometimes we tend to separate the science from the politics, and to ourselves create a barrier of we want to keep them away from us. Do you think this is true, or this is just my personal opinion?
Well, first of all, in my field, it's seen more though as if the policymakers should be the one reaching out. It's not to say that in scientific conferences they shouldn't be invited. Not at all. You can always reach out. I have reached out, and they're like very open to discuss, but they have very little initiative, I feel like. So this is something I will suggest. They are very easy, available, very open to reach out and so on, but they are, not the ones seeking to get involved, to understand, to put themselves out there in that sense. And I don't think though that uh, there is like this real barrier, or like this hermetic between scientists for the sake of science and then politics. On the contrary, I think it's very important that you overlap these two areas. um, I myself have been able, well, I'm not a policymaker, but I myself, as a social scientist per se, have been able to get involved, and I've seen nothing but big openness of the scientists in regards to their work. So I have, for instance, a couple of weeks ago visited the Barcelona Supercomputing Center, and in my experience, at least there, scientists are extremely open about their work, what they're doing, how they're doing it, about everything in the process. And the scientists are very welcoming in taking you through the whole journey of their work. So I think there's not really a barrier that is created, because I have reached out both sides, policymakers, scientists. I think it is good to always have scientists that reach out or invite policymakers and so on. But this is to say, still, it is the responsibility as policymakers to reach out into these kind of events, or workshops and so on, to understand better, because that's how you build together, a technology and a set of frameworks, or standardizations that are accordingly to what it's been developed. Otherwise, you're developing a technology that requires lots of water, and they're making standards for the amount of, I don't know, electricity. So there's a mismatch, right? And this is like something that, yeah, as you said, it can be, you know, the gap between that can be reduced by overlapping the two fields in that sense. And I
Okay.
think it's always good to invite these policymakers to events like this. So hopefully in the future we see more and more attention of these social scientists in events like this.
Thanks, Nelly. It's Fede here. It's the reason we're here. Can you hear me?
Yeah.
Hello. Okay. So I was wondering, somehow thermodynamics was born because of industrial necessity. So we developed a fundamental physical theory so that we could allow the technological development. Whereas now we are facing an energetic crisis, we have a boom, a burst in many technology advancement, and thermodynamics is a niche field. We have very advanced scientific tools, but they are rarely applied to industrial applications. And even in our field, most spin-off startups I know of, they are about quantum computing, QKD, and now there are like our workshop and maybe few more are interested in energetic challenges. But for example, I know zero startups on quantum batteries or other quantum thermodynamics application? Is it because as scientists we are not actually facing real world problems, or because policymakers don't care about the results we propose?
I think this is something I have encountered in different research centers. They work with very fundamental physics. Like we're studying how this atom moves, or if it can imitate, this action from this other. And when it comes with very like fundamental physics development, I think is when you find the policymakers farther and farther away, because they hardly will be able to see the application of it. But that is not to say a lot of spin-offs are born from research centers. I have seen from ICFO itself, from Barcelona Supercomputing Center, from different ones. So the working with fundamental physics to some point, it somehow, drives policymakers' attention farther and farther away. And however, you see these spin-offs burning out of this kind of research, this kind of development and technology, and that is when it becomes more interesting for a policymaker, because they see more of an immediate impact. So I think, it is a tough call, but again, I am very critical of policymakers in this sense, because it is a field I'm very interested in, and it is one of the ones I criticize the most, because there's so much to be improved, right? And I think it is not for policymakers to left aside technologies such as, you were saying in your case, thermodynamics, that is very, more niche. But yeah, at the end of the day, take into account that also policymakers, as part of a broader agenda, have to follow the interests of whatever the government lines of research and innovation they have. So it can be different if you do this in the United States versus if you do it in China, or if you do it here in the European Union. You can end up having really different reactions to it from different policymakers. So I think they also have a little bit of their hands tied in that sense, but it is often what happens. I don't know how it's something that can be solved, because it should be improved. I'm very critical of it, but it often happens.
Hello, Nelly. Olivier Zrati, I'm one of the co-founders of the QEI, and I happen to be in touch with many policymakers, probably not the only one in this room. What would you advise us to say to policymakers? Because policymakers, they do two things in our field. One is they fund stuff, research or procurement, and the other one is they regulate. So do you think we should regulate this field early on as the technology is not mature enough? What we should do, what we should say to those people? And by the way, a comment on top of my question, policymaker should be investigated with a thermodynamic view, given it's not a single body. It's many different bodies. You have regional, country. Within a country, you've got many different organizations. So there are a lot of moving parts and even Maxwell demons in these organizations. So it's not just one person. It's a mix of people who are influencing each other. So how can we influence that global scene? 3 questions in a row, sorry.
Well, I'm gonna see if I can kind of tackle them all together. As you were saying, is for policymakers, I think, talking from the perspective of making more accurate regulations and frameworks, in that sense, it should be work hand in hand. Physicists and policymakers, because what happens a lot of times, they are not completely aware of the capabilities of a technology, or I think it's important for scientists or researchers to try to explain them, this is what it's capable of doing, and this is what it's not, and this is what may be. Because what we find nowadays is policymaking making frameworks or these structures of regulations for what may be able to be developed, but it's not accurately tackling what is able to do now, or tackling how it can be improved. So it also it's very in the optimistic or in the pessimistic way of what are the possible threats and what are the possible super solutions that an emerging technology can give us. And that I think is something that policymakers shouldn't primarily be focused on, and that is something that scientists and researchers can help them to tackle, to understand right now what is capable of and what it is not. So what is and what is not, it's very important from someone that's developing frameworks of responsible innovation and so on, and especially for policymakers here in the European Union, that they try to standardize amongst the EU members countries. So you have even more and more actors that you are trying to regularize, right? So I think in this sense that is probably one of the primordial actions or like tasks that should be taken upon, trying to really define or redefine what things are and things are not in quantum technologies, but also in different emerging technologies, and allowing them to direct. I think I've always said responsible innovation frameworks. This is much more from the science and technology studies, socio-technical systems. It's very as a social scientist thing, but I think also when we talk about responsible innovation, there are many parts to it, right? Like at the top of our heads, the concept may mean well, not not making harm to people, right? And to not create damage to the environment. But responsible innovation are frameworks that go beyond that, from the experimentation, the design, the deployment. And I do think that researchers themselves have a role in this area. Some may agree or some may disagree with me. This is my personal opinion, but I do think that there is a very important role of the researchers and the scientists in the part of the policy making area. That's not only for policymakers, and not only for social scientists, not only for the responsible innovation frameworks. Like it seems very far or probably very outside of the scientific field in which people are used to, or like in the STEM community they feel like they don't fit. But I think it's particularly the ones that have the most important insight. So it is to me primordial, first of all, for also scientists working in the emerging technology to also have a role in the policy making process, at the very least in a small part, but there is a very important role. That's I think what I mean. I don't know if it was clear or did I not answer the other questions?
Yes, thank you. We kind of have to move on, so
Yeah,
I think
we're
the
past the
discussion can
time
continue
now,
tomorrow.
but I'll be happy to talk with everyone tomorrow as well. So I'll be able to see you.
Thank you very much, Nelly. Let's applaud her
Thank you.
again.